All right. So what we were talking about the other day. Basically, anytime we have any attractive forces between molecules is what's going to cause phase changes to happen. And since we know that everything can go through phase changes, you can have everything can be a solid, a liquid, or a gas if you make the conditions right. There must be some sort of attractive forces between molecules. Otherwise, they'd stay as a gas. Right? If there were no intermolecular forces, everything would stay as a gas at all times. Obviously, that's not the case. So what are these intermolecular forces and what causes them? Well, to some extent, gravity, but it turns out gravity is a really weak force. It's not very strong over large distances, and it's not very strong compared to the other three fundamental forces. So gravity, we kind of ignore in chemistry. For the most part, until you start getting into like geology and geochemistry or astrochemistry, we kind of ignore gravity. And then there's the other two. Who can name the other three fundamental forces? Or give me one of them. Weak and strong nuclear force. Good. Those are two of the other three. As their names suggest, those don't really start playing a role until you get to the size of a nucleus. Basically, they're really, really strong forces, but they decay really, really quickly as your distances get larger. So you have to be within about the size of a nucleus for them to matter. Which is why they didn't think that they existed until the Manhattan Project, basically, until Marie Curie started putting forward some of the fundamental research behind radioactivity. So what's the last one? Got gravity, strong force, weak force, and London dispersion is a good guess. So somebody else? Magnetic forces, electromagnetic forces. So basically everything that has to do with charges. Everything that has to do with charges is what we care about most in chemistry. That's why we're always looking at electrons when it comes to talking about forces, right? Or when it comes to talking about bonds. And that's also the forces that, for the most part, are going to govern our phase changes. Right? So covalent bonds, ionic bonds, those are really strong forces. They're strong enough to cause things to stay stuck together. And so we call those intramolecular forces, or just the bonds. Right? But what causes an ionic compound to form? We have sodium chloride. What holds it together? Positives and negatives. What's the charge on the sodium? +1. And what's the charge on the chloride? -1. Right? So an ionic bond is really just these two charges sticking together. Opposite charges attract. It turns out all of the intermolecular forces we're going to talk about are basically smaller versions of the same thing. Right? So they're weaker versions that occur when we have a polar molecule. So review this again. What's our criteria for a polar molecule? Oh, something about electronegativity? Say it again, Brady.
Is it a value 2.4?
Value of 0.4. What about a value of 0.4? Polar molecules need two things. Asymmetry, good. And polar bonds. And that's where the 0.4 criteria comes in. And what did a polar molecule really mean? If we had asymmetry and a partial charges, good. So basically asymmetry and polar bonds, like for instance, hydrogen to a chloride, that's a covalent bond, right? Because we have hydrogen as a nonmetal, chloride's a nonmetal. We look at their electronegativity values. I think hydrogen's like 2.1 and chloride's about 3.0, if I'm remembering correctly. What that means is that gives us polar bonds. And it also means that we've got some of that asymmetry, where part of this molecule is going to be positive and part of this molecule is going to be negative. Which side of the molecule is positive?
No, it's
Hydrogen. Just because I hesitate, don't second guess yourself. Right, and we use that lowercase delta symbol to represent a partial charge. All right, so the fact that this has a difference in charge between both sides is what, by definition, makes it a polar molecule. Or it's also sometimes called a dipole. Anytime you have a dipole, you can have intermolecular forces. Right? Intermolecular forces happen when you have dipoles, because when you have a dipole, it's a lot like having a magnet. Because part of your molecule is partially positive, part of your molecule is partially negative. They're going to tend to stick to other molecules in a way that causes their charges to line up. Right, so it really is just like if you had a whole bunch of magnets. Those magnets, you have to have them facing the right way or they're going to repel each other, right? If I tried to line up another hydrogen chloride molecule so that the chloride was facing like this, there's still going to be an interaction there. But is it going to be an attraction? No. But what happens when you try to take two magnets and force the wrong sides close to each other? They flip around, right? One of them flips around, whichever one you don't have as good a grip on flips around. So if we tried to make this happen, it's going to flip around and you're going to wind up with it turning around to make it an attractive force. Right, so for that reason, we don't really talk about repulsive intermolecular forces, because almost always there's going to be just a quick reorientation is going to cause them to become attractive forces. So pretty much all of these intermolecular forces that we care about are attractive forces. All right, what's one thing that makes magnets stick together more? What could you do with the magnets to make them more attracted to each other? Put them closer. There's a limit to how close you can get them though, right? Like once they're touching, they're as close as you can get. What else could you do to make the attractive forces stronger? You could get more molecules. That's one way to do it. If it's an electromagnet, we could put more electricity into it. That would make the magnet stronger, right? Or what's the other way you could make a magnet stronger? Or swap it out for a different magnet, right? Make the charges stronger. So the strongest intermolecular forces, it's really kind of a semantics. What separates ionic bonds from intermolecular forces, because this is a really strong attractive force because you've got a +1 and a -1. But what about if we made it magnesium oxide? Is that going to be a stronger force? Yes. Or a weaker force? Stronger charges means double the charge means double the attractive force. And we actually doubled both charges. So it's actually 4 times the attractive force. What if we changed one of them, but not the other? What's your intuition say? We can show this if when you take physics, so we can actually look at the equations here. But if we doubled, let's say we looked at Na plus and oxide with a 2-. How does that compare to these two? How does it compare to NaCl?
not the same.
It's not the same. It's not the same charges. We doubled one of them, but not the other. The anion is a higher charge. Does that make it more attracted or less attracted? More attracted. I'm going to butcher the actual equation here, but basically the electromagnetic force has to do with charge 1 times charge 2 over the radius squared. And there's a constant in there somewhere too. Capital Z is what physics uses for charge. you double one of these charges, you double the force of attraction. If you double both of them, you actually increase the attractive force by a factor of 4, right? Because you double the force and then you double the force again. So this attractive force would fit in between these two, right? Stronger the charges, the larger the charges, the stronger the attraction. Right? And that applies to our intermolecular forces as well. The strongest type of attraction is actually an ionic bond. After an ionic bond, though, if you don't have a full charge to compare it to, the strongest type of attractive force you can have is called an ion dipole attraction. And an ion dipole attraction is exactly what it sounds like. You don't have two ions attracted to each other. You have one ion and one polar molecule. So, for instance, sodium with a positive charge is just going to look like a sphere. It's going to be surrounded by, if you put it in water, it's going to be surrounded by water molecules. They're all going to arrange themselves so that the oxygens are facing towards the sodium. Right, and it overall, on average, it's going to kind of look like an octahedral shape. If you think back to your Vesper geometries, octahedral shape was when you had as many things as possible around the central atom, right? When you had six bonds around that central atom, you couldn't really get any more than that because we started running out of space, right? So basically, you can have 6 water molecules all arranged in this octahedral shape around an ion. Right, and that's going to be a really, really positive attraction. That's going to be pretty strong attraction, which is one of the reasons why sodium chloride dissolves in water. So for sodium chloride to dissolve in water, we have to break a bunch of those ionic bonds, right? And I just got done telling you how strong ionic bonds are. Right, so NaCl solid going to Na plus aqueous and chloride aqueous. Why would it do that? That has to break an ionic bond to do that, but we get to make a whole bunch of these partial bonds. These ion dipole attractions are not as strong as an ionic bond, but we get to make a ton of them. Because then what's going to happen with the chloride? Chloride's going to do basically the same thing, right? What's going to look different with the chloride? Yeah, we're going to flip these water molecules around. Each of these water molecules has a positive side and a negative side. Right now, with the sodium, they're all arranged so that the negative side is pointed towards the sodium because the sodium's positive. If we flip the sodium to be the chloride, all of our water molecules are just going to flip. So they're all going to look like this. Where you have all of these, and really it's going to be what kind of like one of the hydrogens is pointed towards the chloride. It's not really just like both hydrogens kind of like randomly pointed there. The strongest positive charges on a water molecule are going to be where the hydrogens are. And so they're going to kind of orient themselves that way. Right, so that's our strongest intermolecular force. You can have cation dipole attractions, anion dipole attractions, but in general, we're just going to call them ion dipole attractions, ion dipole interactions. Does anybody know what happens to the boiling point of water when you dissolve salt into it? It lowers the freezing point. It increases the boiling point of water. Because if you're dissolving salt into water, you're adding these attractive forces. You're making the water molecules stick together better by adding all these attractive forces. All right. The other types of forces are what are called van der Waals forces, which are the forces that only occur between neutral molecules. So anion or ion dipole attractions are kind of their own category. They're not ionic bonds. They're not van der Waals forces. Incidentally, this is the same van der Waals that came up with the van der Waals gas equation, because van der Waals was studying interactions between molecules. And he's the first one that said, well, you can't really assume all interactions between gases are zero because they have all these attractive forces. Right? So this is the other, probably what van der Waals did that is more important, is he categorized these forces between neutral molecules. All right, and so the three main categories are dipole-dipole attractions, which you can tell by the name what that is. What is a dipole-dipole interaction going to be? Two dipoles attracted to each other. So basically this, the HCl we already used as an example, that's a dipole-dipole attraction. However, the other two are also kind of like specialized cases of dipole-dipole interactions. Hydrogen bonds. So let's talk about dipole-dipole attractions in more detail first. So this is just another figure that looks at the attractive versus repulsive forces. The blue dotted lines are the repulsive forces, and the red lines are attractive forces. You can see that in general, you can usually line it up so that your red lines are shorter than the blue lines. You're always still going to have those repulsive forces as well. But because those of that 1 over that force equals charge 1 times charge 2 over radius squared. Radius is the distance between the two charges. So as your distance increases, this force disappears pretty quickly. And so that's why, as long as things are aligned correctly, there's a lot more attractive forces than repulsive forces. The repulsive forces are still there, but they're a lot smaller, as long as all your molecules are facing the right way. Same as a magnet, really, right? All right, and so what this looks like is if we look at similar sized molecules that are more or less polar. As molecules get more polar, they're going to have higher boiling points. As you increase those intermolecular forces, it gets harder to take them from being a liquid to a gas. And usually also their boiling or their melting points tend to be higher as well. But the one thing that goes really predictably is their boiling points. It's like propane. Propane is a totally nonpolar molecule. It doesn't have any polar bonds to it. So propane looks like this. And carbon and hydrogen was sort of our definition. That's kind of our delineation between polar and nonpolar, right? We said carbon to hydrogen is nonpolar, and anything that's more polar than carbon and hydrogen is a polar bond. So this is our definition of a nonpolar bond, really. And it's got a boiling point at about 231 Kelvin, which is what in Celsius? Roughly.
Negative. No.
40?
Like 40.
About minus 40. If we look at something a little bit more polar, like dimethyl ether, it's about the same size, except put an oxygen in the middle instead of a carbon. Now we have polar bonds. Do we have asymmetry?
Yeah.
I love when I ask a 50-50 question, I get both answers. How did we define symmetry? Think back to polarity in the Vesper geometries. What is it? What is the electron geometry on the oxygen? How many electron groups does it have taking up space? It's got 4 electron groups, which makes it tetrahedral. Which if I redrew this, focusing on the oxygen, does that have asymmetry?
Yes.
Yes. Because we said asymmetry was basically if any one object attached to your central atom was different than the others, then it's asymmetry. So in this case, even though I can draw it this way and make it look symmetrical, if we think about it in 3D, it actually looks like this, and part of this molecule is going to be positive and part's going to be negative. Which side's going to be negative? Yeah, centered, the negative charge can be centered around the oxygen. And on the other side of the molecule, you're going to have a positive charge around those 2 carbons. So this is a polar molecule, which is not true of the propane. And if you look at the boiling point is about 17 Kelvin higher. Still less than 0. But basically, as we get more and more polar, this unit right here, this dipole moment, is basically a measure of how big these partial charges are. The larger the dipole moment, the more polar the molecule. And what we can see as we go down the list here is as they get more polar, their boiling points increase pretty reliably. Right, you might be wondering why they picked these molecules in particular, because these are not molecules that most of you have ever heard of, right? They picked these very carefully because none of these have the next category of intermolecular forces. So they're trying not to muddy the waters by picking these molecules. A lot of things that we have personal experience with don't just have dipole-dipole interactions. They have a subcategory of dipole-dipole interactions called hydrogen bonds. All right, and so hydrogen bonds are basically if you take any of the 4 most electronegative elements and have them make a covalent bond with hydrogen. Anybody remember what the 4 most electronegative elements were? Fluorine was number 1. Oxygen,
Chlorine.
not sulfur, chlorine, and nitrogen is actually more electronegative than sulfur is. Sulfur is fairly electronegative, but it's not one of the big 4. So nitrogen, oxygen, fluorine, and chlorine. If you put any of those 4 with hydrogen, if you make a covalent bond between any of those 4 and hydrogen, you get like into a whole nother realm of dipole-dipole attractions. They're like an order of magnitude stronger than regular dipole-dipole attractions. Any guesses as to why hydrogen is so special that way? It's really simple. You're on the right track. What about it makes it simple? 1 proton and more importantly, 1 electron. So once you make a covalent bond with hydrogen, does that hydrogen have any other electrons other than the ones that are in the bond here? They're all part of the bond, right? And so if you make a bond between hydrogen and one of those big 4, the Mount Rushmore of electronegativity, then basically all the electron density is pulled away from the hydrogen and it doesn't have anything left. So we use sharing a bed with a sibling as an example for electronegativity, right? The oxygen is the blanket hog. This is like if you're trying to share a bed with a sibling and you only have the 1 sheet. There's not another blanket. It's like it's not like you still have the fitted sheet that you can be holding on to when they pull the duvet over off of you. You're like just totally out there now, right? You have no coverage anymore. That is what's going on with these hydrogens. You basically have an exposed nucleus, which makes it a much stronger interaction. because there's no other electrons to get in the way once you make that covalent bond. Right, so it's still technically just an intermolecular or just a dipole-dipole attraction. But if it's hydrogen to one of the big four, you get an even stronger intermolecular force that we call a hydrogen bond. Right, so some molecules can form hydrogen bonds and some can't. Excuse me. Which of these can form hydrogen bonds? Can the C2H6? Is that even a polar molecule? CH3CH3? That's not polar. It's not polar. It doesn't even have any polar bonds, let alone a hydrogen attached to one of the big four. What about ethanol? The next one underneath it. Yeah. Yeah, you've got two polar bonds in ethanol. Oxygen to carbon is a polar bond. So we know it can have dipole-dipole interactions, but even more important is that it has an oxygen to hydrogen bond. That means it can make a hydrogen bond to other molecules. And hydrogen bond is kind of a confusing name. I get that. When we say a molecule can make a hydrogen bond, we're talking about intermolecular forces, not talking about the covalent bonds that are part of the molecule. Right? It seems like, oh, well, ethane has this, it has hydrogens and bonds with carbons. Of course it has hydrogen bonds. But when we say, does it have hydrogen bonds, we're specifically talking about intermolecular forces. So this doesn't count. What about methylamine, CH3NH2?
Yes.
Yep, we've got nitrogens with hydrogens attached to it, right? What about if I go back to that molecule from the last slide, that dimethyl ether? It's the same formula as ethanol.
But none of the O's and the oxygen.
But the oxygen is not attached to a hydrogen. So this is a polar molecule that has oxygen and hydrogen in it, but it can't make hydrogen bonds. Same formula, what's called an isomer, can make, because the oxygen and the hydrogen are directly attached, we can make hydrogen bonds. I know it was a whole 2 slides ago, and I'm asking you to recall a random number. Anybody remember what the boiling point was for this one? 240 something, 248?
Yeah.
Ethanol is about 78 Celsius. So about 350. Same formula, same atoms in a slightly different arrangement, and we get a boiling point that's 100 Kelvin higher. Asen?
Is the reason we measure like OH and the pH stuff, is it's not wrong? It's like what constant?
You're flipped correlation and causation a little bit. We measure pH and pOH because that oxygen-hydrogen bond is so polar that it can be broken. So you're on the right track. They're related, though. All right. The last one is both the simplest and the most complicated. It's the simplest because anything with electrons has this next type. But it's the most complicated because it's a little abstract. So let me go back. We have dipole-dipole interactions. We got hydrogen bonds. There has to be some sort of attractive forces between these nonpolar molecules too, right? Like nitrogen, Lewis dot structure looks like that. Is that a polar molecule? No, because nitrogen to nitrogen can't be a polar bond, right? But can you have, does nitrogen exist in a liquid state? Everybody's heard of liquid nitrogen, right? So we know it can go through a phase change, but it's totally nonpolar. That means there must be some attractive forces even between nonpolar molecules. And that's this last category. These London dispersion forces, use LDF for short. London dispersion forces happen anytime you've got electrons in a nucleus, which is everything, right? Everything has electrons in a nucleus, even if it's a nonpolar molecule. If you have electrons in a cloud around a nucleus, so helium's a really simple example to look at. A helium nucleus or a helium atom is going to look like this, right? 2 electrons around a nucleus that has 2 protons. At any given point, there's a possibility that both of your electrons are on the same side of the atom. Right? If they're just bouncing around like crazy, they're existing as a cloud, really, but they're still also paradoxically point charges. There's a possibility that you get both electrons on the same side of the molecule at the same time. And if you do that, you temporarily have a dipole. It's basically you're taking a nonpolar atom and shaking it enough so that it becomes polar for a second. And what happens, so they call that a temporary dipole or an induced dipole. But if you do that, if a helium atom does that, and it happens to bump into another helium atom at the same time, then that other helium atom is going to be influenced by the fact that your first helium atom has 2 electrons on the same side. If one of your helium atoms has 2 electrons on the same side, that's going to push away the 2 electrons on the other helium atom for a second, for less than a second. But what that means though is that there are some attractive forces because these electrons are kind of sloshing back and forth. Think about trying to carry a big, I don't know, plastic bin full of water. So on average, the water is evenly spread over the bottom, right? But as you're carrying it, it's going to slosh back and forth. And at that moment, when it sloshes to one side, it's going to be heavier on that side than the other side. That weight is kind of like the charge. When it's heavier on one side, you've got extra electrons on that side. Right? And so that means even completely nonpolar molecules like nitrogen or helium have some attractive forces. Right? So how am I going to test you on this stuff? Well, I guess before we get to that, the last piece of this is how do we know how strong these London dispersion forces are? We need to know how easy it is to move the electrons back and forth. What's going to affect how polarizable something is? What's going to affect how much the electrons slosh back and forth?
How many electrons?
How many electrons are there? So is more electrons going to make it easier to slosh back and forth or harder? Yeah, if we think about it like actually spilling the water out the top of our bin that we're carrying, the more water you have, the greater chance that it's going to slosh over the side, right? So more electrons means more polarizable, means more attractive forces. So what's the easiest way if we're looking at a molecule to judge how many electrons it has? We could count them. Counting is hard. We didn't get into the sciences to count things. Bonds, really atomic mass is actually a pretty good indicator though, right? The bigger the atomic mass,
Or
more electrons, right? It's not a 1-to-1 because there's those neutrons in there and that throws things off. But in general, bigger your atomic mass, the more electrons you have. The more electrons you have, the stronger these London dispersion forces. Right, so if we just look at the halogens are all present as diatomic molecules. If we look at their molecular weight versus their boiling point, we can see a really clear connection. Fluorine boils at 85 Kelvin. Chlorine is at 238 Kelvin. Bromine is a liquid at room temperature. It boils at 332 Kelvin. Iodine is a solid at room temperature. It doesn't boil until you get up to 450 Kelvin. Really clear trend. And we see the same thing with the noble gases. Helium boils at 4.6 Kelvin. Really cold. All of these all these noble gases are gases at room temperature, but their boiling points go up and up and up.
How much would it take to boil uranium?
A lot. I don't know what the boiling point of uranium is.
Let's find out.
Well, in metals, we haven't touched metals yet. Because metals have their own type of bond called metallic bonds that behave a little bit differently than covalent bonds or ionic bonds.
400 degrees Celsius. 120 uranium.
Okay, there you go.
Oh, so we can do that here, right?
How much? 2,000 or 1,000?
4,000.
4,000. Yeah, we can't do that here. Bunsen burners will get up to about 1,800 Celsius.
So like.
So some of, yeah, an industrial fort. So one of the groups at LTCC, their research project was building, they're trying to make metal alloys. And so they had to build a forge out of cinder blocks and Bunsen burners. They were able to do it. I think they were able to get decent results. I'll see their presentations next week and I'll be able to report back to you, but. All right, so. How can I test you on this stuff? This is all pretty abstract concepts. There's vocab and concepts, but also I'm going to ask you things like, here's the system. What types of intermolecular forces are in this system? You've got water. What types of intermolecular forces does water have? That'll be on the test. If not, I don't have a quiz planned because we really haven't covered that much material this week. So 2 weeks in a row without a quiz. How lucky.
I mean, we're all very happy.
Dipole.
So here's our categories from weakest to strongest. What's present in liquid water?
Hydrogen bonds.
Hydrogen bonds.
Dipole.
If you have hydrogen bonds, you also have dipole because hydrogen bonding is a type of dipole.
You have to like say the, or just one like override the next.
I would like to hear both of them. So we've got hydrogen bonding and dipole in water. What else do we have? Do we have dispersion forces?
Yes. All of them. Oh, all of these.
Everything has dispersion forces. That's your easiest answer for these. Everything has dispersion forces because everything has electrons.
Said dispersion. How many points of vectors?
Depends on the way the test. We'll look at the test here in a few minutes.
There was 3 answers. We all got dispersion.
Probably half credit,
Yeah.
especially since you only got the easy one. If you're just going down the list and you just write London dispersion for everything and move on, I see where you're going with that. I mean, you're gonna get one of them right probably,
Hopefully.
and then half credit on the others. Does it have any ion dipole forces in just water?
Is there ion dipole? I don't feel like there's anything else in it. It does not have.
If there's nothing else in, well,
I'm not sure.
this is one where if you defend your answer properly, there's 2 right answers here. I normally would be saying no, there's no ion dipole forces. But if you said yes, because water splits into hydronium and hydroxide as an equilibrium process, there's technically ion dipole forces too. There's just not very many of them. But I would accept that as a full credit answer if you explained it.
Statistically insignificant evidence to decide that there are.
The best possible answer would be to pick the top three and then when you get to the bottom, say, there are some present, but they're lost in the sig figs. Right, they round up. There's such a small number of them. That we can ignore them. Lost in the sig figs is what we could call the first half of this class. All right. There was another way. Oh, the other way that I test this is basically by asking you to rank things by boiling point. From lowest boiling point to highest boiling point. So if I said rank propane, and you don't need to have these memorized to do this. All three of these are pretty close to the same atomic weight. All pretty close to the same number of electrons. But we can rank them. What's going to have the highest boiling point out of these?
The middle.
Why? Is it an ion? None of these have any ions, right? So no ion dipole. If any of them did. This one has the hydrogen bonds because it's got the oxygen directly attached to a hydrogen. That's the right answer. You look for the strongest intermolecular force that's present, and that one's going to have the highest boiling point. Deal? That's the so these are close to the same mass. These two are the same mass. If they're the same mass, what's more so good? There are two things to look at, two variables. If they're all the same type of intermolecular forces, then you look at whatever's biggest is the highest boiling point. If you've got different types of intermolecular forces, whatever has the strongest intermolecular forces is the highest boiling point. Right? So oxygen to hydrogen bond means you can make hydrogen bonds with this bottom one. So this is going to be your strongest intermolecular forces, even though it's the same weight as these other two. So if we're ranking these, there's our highest. There's our lowest. And there's our middle. Because hydrogen bonds out of the intermolecular forces we have, hydrogen bonds is the strongest. Nothing in here has any ion dipole forces, so we don't need to worry about that. So then we just look at, okay, do any of them have hydrogen bonding? Yes. So flip it the other way. If everything has the same strongest force, so there's 3 different alcohols, only one of which you can drink and none of which you should be drinking. Methanol is camp stove fuel. This is rubbing alcohol, isopropyl alcohol. This is ethanol, drinking alcohol. These two will kill you and make you go blind first. So don't do that. Which of these, if they all have the same type of intermolecular forces, which they do because they all have oxygen to hydrogen, right? You go to the biggest molecule, which is isopropyl. Then the ethanol, then the methanol. if you have the same size molecule or close to the same size molecule, but with extra OHs. Is that one has, they all have hydrogen bonds, but this one has more hydrogen bonds, right? So this is going to be the highest one. This is called ethylene glycol, better known as antifreeze. Antifreeze boils at well over 100 Celsius. So compared to these others, this one's going to be our highest boiling point. Right, so how do you decide if I'm not gonna ask you trick questions on the test. There's gonna be one where they all have the same type of intermolecular force, and you just have to look at which one's biggest or which one has the most of those groups. And then there's gonna be one where you have to decide where they all have different strongest intermolecular forces. Right, I'm not gonna mix and match those variables like we did with the periodic trends, right? The most important thing, well, there is like a crossover. There are non-polar molecules that have a higher boiling point than water because they're that big. Like bacon grease is a good example. It's a non-polar solid or liquid, depending on its temperature. It boils well above the boiling point of water just because it's a giant molecule. Fats in general are called triglycerides. They have a general structure that looks like, let's see, carbon. It looks like that. And then CH2, like 17 and a CH3. And you do that 3 times. It's technically a polar molecule because it's got these carbon oxygen groups in the middle called an ester. So this is called a triglyceride because this backbone here that links everything together is called glycerol. So this giant molecule is mostly non-polar. It has a little bit of polar bonds, definitely no hydrogen bonds though, but it's going to boil well above water just because of it's huge. So there is a crossover where the most important thing is how big it is, and rather than just which level of intermolecular forces you have. So I'm not going to ask you trick questions like that. It is worth noting if you want to study stuff like this is why if you're going to go into studying biology, you have to take organic chemistry and then biochemistry, because organic chemistry teaches you how to draw these structures, and then biochemistry is all about how does the body or a cell make this and use it. Turns out this is a really convenient way to store energy in a long-term way. And what happens is there's an enzyme that comes into these big long chains and chops off two carbons at a time to make one of the precursors to the electron transport chain. Anybody want to guess what molecule that is? Who took the AP Bio test? What feeds into the Krebs cycle from glycolysis? What is it? It goes pyruvate, and then pyruvate gets turned into ATP, but there's a lot of intermediates before you get there. It's the other one. You chop one carbon off of pyruvate and attach it to a CoA, and you get acetyl-CoA. You chop 2 carbons at a time off of this and attach a CoA, and you get acetyl-CoA. And so you can feed into the citric acid cycle without having any sugars present if you have fats. Also, the problem with that, though, is you wind up generating a lot of what are called ketone bodies by doing that, because your body needs glycolysis in order to regenerate some of the molecules in this pathway. And so what happens is if you just eat fats and proteins, you wind up producing extra ketones in your body, and the most significant of those Kind of. Now you wind up making this molecule, which is called acetone. Your body will actually produce acetone. If you go on a truly zero carb diet for an extended period of time and go into what's called ketosis, your body actually starts producing acetone and methylethyl ketone. And you can actually smell it on someone's breath. If they've been on a truly zero carb diet for like a month, it's really not very healthy long term. It's a great way to lose weight. If you can stick to true zero carb diet, but you really need some amount of carbohydrates because that basically resets some of these cycles, allows the body to get back to regular energy production for a little bit, and then go back into breaking down fats. All that is not really relevant to the test at all, but I think it's kind of interesting. Everybody likes nutrition, right? Because it's always interesting to know what you should be eating and the chemistry behind it. So not just 12 rice bowls a day, but also not just 12 slabs of bacon a day. Moderation in all things, including moderation. All right. When we're talking about phase changes, here's our last topic, and it's one we've touched on already when it comes to intermolecular forces. Last thing to talk about here is phase change. And we're not going to do too much with math of phase change or energy of phase change. We'll talk about it a little bit qualitatively. So what typically happens when you go from a solid to a liquid? Are you going to increase intermolecular forces or decrease the number of interactions? When you go from a solid to a liquid. Yeah, because in a solid, everything's kind of locked into its most favorable state. And if you go to a liquid, everything's still kind of close together, but they're able to move around a little bit more. Right, so in our magnets example, solid is when all the magnets you have are all stuck together in one big clump and everything's aligned so that all of the positives and negatives are lined up properly. If you take that and you shake it hard enough, most of them are still going to be stuck together, right? But some of them are going to move around a little bit. That's kind of what a liquid is. A gas is when you then take that and you shake it hard enough that every magnet flies apart from every other magnet. When you go from a liquid to a gas, you remove all intermolecular forces. You have to break all of them to do that. Right. So in general, that's why gases are present at high temperatures. Solids are present at low temperatures. Because what happens when you increase temperature? What are you really increasing? Kinetic energy of those molecules, right? How fast they're moving. Faster they're moving, the less they're going to stick together. All right, so I think I've thrown this slide up here before. But basically, this is just a vocab sheet. What's more interesting about phase change and what is worth spending more time on is the different conditions, right, that allow us to change whether or not we see a liquid or not. Right. So in general, for the most part, they're terms you've heard before. Everybody's heard about condensation. Evaporation and vaporization mean the same thing. If you said evaporation, then I would give you full credit instead of vaporization. Means the exact same thing. Melting and freezing. Sometimes we call freezing fusion because it does sound weird to talk about we tend to use the word freezing in everyday life to only refer to water, right? Or food products in general. But technically anything solid is frozen. That's just a weird way to think about it though, right? So sometimes we use the term fusion instead of freezing, but it means the same thing. It would, because, yeah, technically the table is frozen or solidified bacon grease is frozen. Frozen bacon fat. That does seem weird, right? Not technically wrong. And then there's these other two that we have less experience with. We talked about them a little bit though, right? What was our good example of deposition? Gas to solid.
It wasn't like. It was a window, the sound.
Had to do with water going from a gas dissolved in the atmosphere to a solid. Snow
Yeah.
or frost.
Yeah.
Frost is just deposition happening at ground level instead of in the upper atmosphere. Sublimation is when you go straight from a solid to a gas without hitting a liquid in between. Right, and so a good example of that in the winter here is if we never get above freezing, but we still have less ice at the end of the day. On the roads, for instance. We may have never gotten to get liquid water, but somehow that ice disappeared. Or if you've ever had an ice cube tray in the freezer for a really long time, the ice cubes kind of shrink, right? Has anybody seen that before? That's sublimation happening over time. When the ice cubes first freeze, they fill the ice cube tray and they're stuck to the sides, right? And then if you leave it in there for 6 months, you come back and they're like, it's like shrunk away from the side a little bit. That's sublimation happening. And I guess freezer burn is an example of deposition as well. Right? Or if you've ever put a fresh ice cube tray into the freezer and you come back and the entire inside of the freezer has ice crystals on it. That's because the water from the ice cube tray vaporized and then deposited. This is why you don't put boiling water in the freezer, because you get big amounts of ice crystals forming all over everything. All right. Won't get into that. We're gonna skip the energy part. We already talked about vapor pressure. All right, we're gonna go off slide. Because we've talked about some of this stuff before, and the main thing I want you to remember about phase change is the phase diagrams. Anybody remember what the two axes were?
It was temperature and pressure.
Temperature and pressure. They always look close to the same. It's always temperature on the X, pressure on the Y. So if you're in the way that I'm going to test you on this, I guess let me double check that before I say that. Let me look at the test. Because there's two ways I've done this before. That's why that doesn't make sense. There. All right. So the way that I'm going to test you on this is I'm going to have you draw this and label the parts on it. Right? I'm just going to say draw a phase diagram. And I'll give you some specifics about it. But in general, they're always going to have the same shape. There's a few things that can change. The specifics of where these points show up and the slope of this line dictate a lot of things. Right? But it's always going to be pressure on the Y, temperature on the X. And if, as long as you can get that and you have the basic shape right, you can logic your way through the rest of it. How do I know which phase is which? What's the easiest phase to label?
Yeah, that's all. Yeah, that's got.
I would say liquid, because you know that liquid has to be which one?
If it's,
The smallest one and the one in the middle. So you can always do that right off the bat. Right? And then as far as the other two, so you've got a 50-50 shot once you do that. But if you think about it, high temperature favors
yeah.
solid or gas. So if we go this way, that's got to be a gas. This whole section is gas. And at low temperature and high pressure, that favors a solid. Now, one of the other things that I ask about is, one of the specifics I can give you is, I can tell you where this point is. Does anybody remember what this point was called?
It was try something.
Try something.
Where
Even simpler than that.
Where you. Actually,
It's the triple point, where you can have all three phases at the same time in equilibrium. So I could do something like where if I said that the triple point is this particular set of pressure and temperature, and you could label it. The other thing I can do is I can say for a substance that is more dense as a solid than a liquid, or less dense as a solid. So water is a good example. Is water more dense as a solid or a liquid?
It's like less than solid.
It's less dense as solid. How do you know?
Because
Because ice floats. So if it's more dense as a liquid. So let's say we started right here. Doesn't matter what the pressure and temperature is. If we increase the pressure, what's going to happen? If we keep it the same temperature, if we increase the pressure, it's going to do that, right? We increase the pressure, it's going to go from a liquid to a solid. If we increase the pressure and it turns into a solid, is that more dense as a solid or more dense as a liquid? That would make it more dense as a solid, right? We pushed on it and it turned into a solid. So what must be different if it's water instead?
It's going down. It's going to the water.
Yeah. So if it's more dense as a liquid, that means we could start as a solid and increase the pressure and it becomes a liquid. So that's true of water. If you take ice and you squeeze it, it turns into a liquid. Which is, anybody seen the YouTube videos where you put a water bottle into the freezer and then you take it out and you uncap it and it freezes all at once? You have to have the right type of bottle for that, but basically what you're doing is forcing it to stay at a high enough pressure that it won't freeze. And when you uncap it, you remove that extra pressure and it freezes all at once. If it's more dense, so basically the slope of this line is the other piece that you can really, it's always going to be solid, liquid, gas in the same order. If it's a positive slope, that's more dense as a solid. Most substances look like that. Water is kind of the exception in that it has a negative slope. Water looks like that. All right, so what is this last piece? What is this piece right here called? Anybody remember? Point super something? Super means past that point. This is called the critical point.
Yeah.
Good. And if you go past the critical point, you can be said to be supercritical. Plasma technically is a different thing. They oftentimes are the same because they happen under the same conditions. A plasma means that you have enough kinetic energy that your electrons are not bound to the nuclei anymore. Which typically means you're also past the critical point. But they're slightly different. So this point, once you get past the critical point, we call that the supercritical fluid. It's not really a liquid, it's not really a gas. It has enough energy to be a gas, but not enough space to be a gas. If you picture taking a gas and pushing it down unto the point where it's all of your molecules are close enough to be a liquid. Right? So it kind of behaves like both.
How close do scuba tanks take to that? How, like, what PSI would you have to get to?
It depends. This critical point changes depending on what the gas is. So you can actually make supercritical fluid out of CO2 pretty easily. That's actually how they do make a lot of essential oils, and how they make decaffeinated coffee. Is you make supercritical fluid out of CO2, and then you remove the extra pressure, and then all the CO2 just evaporates out. Supercritical CO2 makes a really good non-polar solvent because it's totally non-toxic and it evaporates really fast as soon as you remove the extra pressure. So the other thing, other non-polar solvents tend to also be flammable or carcinogens. So for instance, there was when recreational weed first got legalized in California, there were a bunch of people that were making weed extractions, THC extractions and CBD extractions using butane. The problem with butanes are really cheap, easily available, and easy to evaporate non-polar solvent. So it works really well for those extractions, but it also blows up. So people were, blowing up their garages all the time and stuff like that. And they had to limit how big of a butane bottle you could buy for a while. All of the stuff that's now that actual chemical engineers and chemists have gotten involved and started making all those tinctures and stuff, they all use CO2 as their liquid because it's really, really safe and also not a carcinogen and also really, really cheap. You just have to have the know-how and a system that can handle the pressure, because I believe the pressure you need to get up there is about 4 atmospheres. So you have to have something where like a pressure cooker usually works. But if you're retrofitting a pressure cooker, you need to really know what you're doing, or you're just making a bomb. So don't go cutting up pressure cookers and then expecting it to hold its pressure very well, because pressure cookers improperly modified literally are bombs. Anybody remember the Boston marathon bombing? That was literally just pressure cookers that they welded shut so that they couldn't open, so that the valve, the safety valve, wouldn't go off. So literally a bomb. Don't go doing that just because I told you could make CO2, liquid CO2. There are better ways to do that.
We did that. When we brought the blast shield and we did that.
You really want to get the blast shield out. Oh. All right. I think next week it's if not next week, then during review week. Okay.
We're gonna start nuclear.
We're gonna do nuclear on Monday.
Just stop.